Hey folks, good afternoon. Henry and I are going to be presenting RSpace, which is the storage layer for the RChain architecture. And we released RSpace not too long ago, end of March, as a separate library. So you can use the RSpace library in your implementations if you so desire. If you like the architecture, you like what you've heard here, feel free to go ahead and create an application or implementation using that library. Be happy to hear your feedback.
Scala only right now.
Yes, it's Scala only right now. All right. So a little bit of background. Greg went ahead and talked a little bit about the history of this kind of technology, right? It's MAP, associative memory. I don't have a lot of notes here. So it's a key value store, and you heard Greg discuss about keys or channels, right? You've got channels, and inside the channels we're storing continuations and patterns and data, and that's really where the machine state for the RChain machine is stored. So it's within the Tuple Space. It's where all the action happens, actually. So a little bit of background about Tuple Spaces. I'm not going to spend a lot of time on this slide because a lot of you heard the earlier talks today. So it's designed to operate in a distributed setting, and it was introduced in the 80s by David Gelernter. And key value pairs are used to store communication and coordination mechanisms between computations, right?
It's really designed to be used in a distributed setting, and it was thought of as like a layer over key value stores that were in distributed nodes of a distributed system.
So it supports three main operations, right? So out, in, and read. And so gets, puts, and reads. Very simple database architecture, right? Base of it. Use the LMDB. It's backed by LMDB. And we have an interesting implementation that allows us to use pattern matching. And the pattern matching we use is actually the matcher that Kyle created for the Roland. We used the exact same code and implemented that match functionality to make RSpace our own for the RChain core architecture. I'm going to go pretty fast here. Not bad, go back. So it has its roots in Special K. Those of you that are familiar with the scenario project, Henry actually worked on a scenario project with Greg. And Special K introduced the idea of storing continuations. And we've taken that learning and that experience and improved upon it as part of the RChain architecture. You want to say something more about this?
Yeah, essentially Special K was a kind of EDSL, an embedding of some of the same ideas you find in Roland. And it was it didn't have a blockchain. The store was a distributed store, and when you went and you put and got data from the store, if the data was not there, or you would be going and looking out across the whole network to see if you could find matches for that. So instead, now we're replacing that mechanism with a blockchain and a consensus model as well. And we have a full language instead of a DSL. So.
Okay. So talking a little bit about Special K's architecture, we have some description here about data, continuations, produce verbs, and consume verbs. The produce verb and consume verb you're going to see later on. We'll go through the function signatures, but we have those same verbs in current implementation of the Tuple Space, and they're essentially put and gets. And then data is ephemeral, and continuations are ephemeral.
You
so
can, to modify, you can essentially choose between persisting the data or having these ephemeral stores. And you've heard about these ephemeral stores where you put something into the Tuple Space, and when you find a match, then it takes the thing out. But there's also this persist flag as well, and that's a persistent put. And for those of you who were there yesterday, I mentioned that when we have a smart contract being persisted, then we're doing a persistent store into our space. And then the ephemeral ones are like the ones that you just heard in the last talk referred to as linear. Linear in the sense that the first person who gets it consumes that thing and it's no longer there. a la linear logic, linear types. So,
yes, Grand Central Station. So Henry and I talked about this, but because the state of the RChain node, in essence, is stored in the tuple space, all the action happens in the tuple space, right? So Rolang doesn't have any ability to create any effects on the machine. It creates all of its effects within the tuple space. So anything you do inside of a Rolang smart contract happens first and foremost inside the tuple space. Mm-hmm. That is where all the machine state is stored. Ultimately, that is where history and rollback will also take place. So when a node gets a new block, it's going to compare the contents of the block with what it has in its tuple space and then update its state in the tuple space to match what it received with the new block. So that's what we're going to be doing soon.
And the consensus mechanism, Casper, will be communicating directly with the tuple space as well. So you'll have Rolang will be doing produces and consumes. And in the initial implementation of Casper, that will be written as Scala code. And it will also be doing produces and consumes into RSpace as well. So
any process on the RChain node that wants to have effects in Rolang or vice versa has to go via the tuple space, because that's where everything is stored. That's where all the action happens. So you've learned about Rolang semantics, right? You've learned about the concurrent execution model, right? This tuple space is what enables all that. This concept of channels, right? That you can have concurrent execution, and because the continuation is stored in these channels in tuple space, execution happens very independently. And if a process is waiting on input, it can just wait in the tuple space until it receives that input.
But I mean, conceptually, like Kyle mentioned, he called channels names, and you can also just think of them in the sort of a key value discipline. And this is just that mapping here. I mean, a channel is a key, and these are the values in the key value database in that sense.
So the main verbs, right? Operating with a given store, we've got consume and produce. So consume searches the store for data matching a given list of patterns at a given list of channels. And produce, which given a piece of data at a given channel, searches the store for matching continuation using the existing data in the store to help satisfy the match.
And those signatures? Are there still?
Signatures are coming up. When a continuation is returned along with the data, the consumer of the library executes the continuation.
But both functions, consume and produce, both return the same thing, which is an option of a continuation in the data if it was matched, right? So.
And we're going to have 2 new verbs coming in future release is checkpoint and reset. And this is again for history and rollback, right?
Yep. There they are.
There they are.
So
talk to those.
4 type variables. 1 for channels, 1 for patterns, 1 for data, and 1 for continuations. So a consumer of the library can use their own types. This was mentioned before. Mike mentioned this in the intro today. We have, in the Rolang implementation, a channel type. And the channel type actually gets used as CPs and As because of the vagaries of the implementation. There is what we call a tagged continuation, which can either be a Scala continuation or a Rolang continuation. Mike mentioned that earlier this morning as well, so that we can dispatch based on which type of continuation is. This supports our ability to run Scala code like you saw with the Standardout channels. Also the FFI that was mentioned earlier is also executed the same way. So, and right here you'll notice that there's an implicit parameter for the matcher. As a library consumer, you would be providing your own matcher as well. This is essentially a type class. We'll get to show that in a second. But you have to have a matcher between patterns and data.
So as Henry just indicated, it's type class-based design. So the RSpace doesn't really care what kind of language you want to support. You provide a matcher, you provide the continuation type, and then the system can take it from there. Right? So it knows nothing about the internals of channels, patterns, data, and continuation. They're opaque to the mechanics of the tuple space. Right? We constrain these things to be things that can be deserialized and serialized using match type classes.
Using the serialized type class.
Serialized type class, yeah.
Yep. All right, here's the match type class. Pretty simple, 1 function. Match takes a pattern, takes a piece of data, and then it returns an option of an A. So in your match function, you can actually process your data. It's a little bit more powerful than just returning a Boolean, saying whether or not it is or isn't a match. We can say, if it is a match, then here's a piece of data back. So you can imagine some arbitrarily complex matcher, a la the one that Kyle has written. So, and the next type class is serialize. Pretty simple. You have a type A. Again, this is like for continuations, patterns, data, and your channels. All of these have to implement this type class. I stole these signatures from the Haskell library serial. Essentially, you can take some A within code and convert it to a byte array. Here, you can take a byte array and you can deserialize it back to the A, although that can fail quite easily. So we return an either of a throwable. Probably we could have an error type, but I didn't want to add too many type parameters at the initial implementation. So there's a bit of an asymmetry here. Dan pointed that out to me yesterday, and I recognized that, and it didn't start bugging me until yesterday when he pointed it out. So in the future, we may actually decide to like encode failure on the encode side, because that would be the right thing to do here. So API changes coming soon. All right, next one. So when you need to provide these instances in scope as implicits when you instantiate the store. We do that just because we expect that you're going to be using the same types with produce and consume. We don't attach implicit parameters to the functions, but instead they need to be in scope when you create the store. And so in addition to providing these in scope, you also provide a directory where you're going to be storing your database files and the maximum size of the database right here as well. So LMDB.
Yep, backed by LMDB. We chose LMDB because of its speed and because it's memory mapped. So that enables the architecture to go to disk as it needs without us having to explicitly manage any of that. We get that for free.
We let Unix do what Unix does well.
Yes,
yep.
That's right.
It's actually performs quite favorably to like things like level DB, which are pretty common choices in the blockchain space. I encourage you all, if you're interested, to go and check out the LMDB webpage. The author of LMDB has provided a lot of really solid information in demonstrating the ways that it outperforms level DB and SQLite and Kyoto Cabinet and Berkeley and all these other classic choices for key value stores. Yes, it is a C library. We get the benefit of the fact that it's already packaged as a jar, so you don't have to worry about bringing on a dependency on a C library. It just is a jar that has the DLL and the dylib and the SO in it for us. So, all right. So this is going to give run through a little example of how it might look if you were going to design a little Scala application to use produce and consume. And we're going to use our own types here. So our channel is just going to be called channel. You can imagine this being like an address booky kind of example. Maybe your groups of friends. So you'd have friends as your string in there, or you'd have family as your string in there, or colleagues as your string in there. Entry here is a compound data type of all name and address. Email is a string, phone is a string. And then here's kind of fun thing. This is the pattern type here. So what we've done is we've designed a kind of pattern matcher where we're going to do queries where we want to match against someone's last name, maybe the city that they live in or the state that they live in. So we create this sum type to represent our pattern. Next slide. Yes, and our continuation here. So one thing you'll notice here is that I'm using Java serialization. This is kind of to troll Greg. He's not here right now, but he's been trolled several times over by this. In Special K, he attempted to use Java serialization and had some horrible difficulties with it, quite righteously. It's a terrible thing to use, and I implore you all never to use it should you actually decide to use this library. But for the sake of the example, it was kind of fun to do. So This is like a simple printer continuation. It implements function one of a sequence of entries to unit. So it's just basically going to take a list of entries and it's going to print them all out in a sort of nice format here. So you could implement any number of continuation types of your own in Scala like this. You potentially, when you're serializing a function, you have to be wary of closing over state, environment capture, the typical things that come with like trying to do mobility on functions, on closures. So it's something to watch out for, but it's doable. It's definitely doable. And this pattern of doing sequence of your data type, this is like the type A that you saw back there, to unit. This is a common pattern in this case because we're asynchronously running these continuations after we've matched on them in the store. So, yes, this is what an instance of that serialized type class looks like when we use Java serialization. Written out painstakingly because I didn't want to incur any dependencies on third-party libraries. There are nice ways to convert this try-catch into an either type, but I'm not using those here. So you can see me, try-catching here, but it's essentially doing the horrible, horrible Java serialization thing. So again, don't do this. Don't do what I did. But so you would do this for your channel, for your pattern, for your data, and your continuation. All four types have to implement serialize so that they can be stored in the database. And this is the match instance for our data type. So we had that entry back there that was the address book. We had that pattern type. Here what we're doing is we're taking that pattern that comes in and we're matching against what we get, the piece of data. So if the last name matches the last name in our data, then we return that as a sum A, just for giving the data back. And the same things with city and state. But otherwise, if neither of these three conditions are satisfied, then we return a none, indicating no match has been found. So this is like what a custom matcher looks like. And we instantiate the store. And we do our first consume here. So what we're doing in this case is we are going to essentially install a query into the store. And we're looking on the channel friends, the key friends here, and we're looking for something where it's going to be an address that matches the city of Crystal Lake. And we're installing that printer continuation in there. So we get back a none because there's no data in the store that already matches this continuation. So now we present a piece of data into the store. Here's Alice. And this is what her entry looks like. Next slide. Another piece of data. Carol. Next slide. Okay, so we're going to produce Alice into the store. This is like sending in Rolang, right? We're sending a message to the channel friends with the piece of data Alice, right? And so because we have Alice, look, she lives in Crystal Lake and she was one of our friends. So she's a match. So what do we get back? We get back this option. Here's that continuation as a function one right there. And then here's a list of all the data that matches. We've only got one piece of data that matches right now. So we're calling that pres1. It's a little helper function here that just runs this by applying pres1 to the input of that function one. And as we can see, it prints out Alice here. So that's an example of a successful match in the produce consume paradigm. Next one. I'm going to go in the opposite direction now. So let's imagine the store is empty. And we're going to first do that thing where we have the piece of data and we're going to send that into the store. And we get back nothing because there's no matching continuation in there. And then we're going to do a consume just like we did before. Actually, this time we're looking for friends with the last name blah blah. So as you can see, we get back the continuation and the piece of data that we just had presented in the store up above. This continuation never even hit the store because it went looking for that match found a match, and just immediately returned it back to us. If we wanted to keep the continuation in the store, we would have to use the persist flag with a caveat. If we did it this way, it would not stick because there's already an existing match in the store. So what would first happen is you would get back your match. And by virtue of the fact that we get back a match, we know, oh, it didn't stick. So then we have to run this again with the same setting, persist true again. And when we get back that none, we know it sticks. You can imagine writing a recursive wrapper around produce and consume to handle that for you. But in this case, there are some dark corners to doing that. So we'll probably be improving this part of the API in future releases. And there's a whole tutorial that does this and more, machine checked, so it stays up to date with the code. I encourage you, if you're interested, to go and check it out.
Should we stop for questions now?
I think we have a couple more slides.
We do. We can keep going, or we can pause for questions before we go into the rollout.
Does anybody have any questions about the Scala example? Curious? Mm-hmm.
Can you give him a mic?
Yep.
Give him a mic.
So just to clarify, in the slide before you mentioned that when you did the produce, it gave you back the contents that was already in the store. Then you had to write it again, but you said you had to change persist to true, but you meant false, right?
Sort of sped through that bit a bit. Okay, so in this example, we're going to start out with an empty store. We're going to put a piece of data in first with a produce. And then we're going to do the query with the consume. So what's going to happen when we don't use persist is going to be false here. The match will happen. The continuation will never go into the store. Okay. Now, in the event that we want to persist, we're going to set the persist flag to true. Okay. We're going to get that one match back. It's not going to have stuck at that point, right? Because there's the match here. So then we're going to do the same call to consume. And persist definitely has to be true the second time. You don't have to technically have it be true the first time, but you definitely have to have it be true the second time. So there's like a kind of late addition to the initial release, this part of it. So there's a few dark corners that really still need to be worked out with that. But it works because Rolang works. So so after you've gotten back a none, that second time, you know it's stuck. Yeah. So you can just write a recursive wrapper to do that and to make sure that you got back that none and you know it's stuck. I wrote the wrapper and was about to hand it out as a library function. And then I noticed that there were some really terrible things that happened when you both were persistently producing data and persistently producing continuations. You can kind of imagine you get these weird recursive things happening that way. So that's a part of the API that still needs to be worked out a little bit. Yeah. Any other questions?
Yeah. No, we'll carry on now and kind of demonstrate this with Rolang.
Yeah, we can just map these pretty simply to Rolang.
Now we're going to relate to Rolang and talk a little bit through our Rolang implementation.
You guys will have probably seen this before. So what is this normalized to? Next slide. That. We've got a 4 up here. So this is what Kyle refers to as a receive. This is a send. This is another send down here. Okay. And so what these are here, this is a call to consume. Yeah. And then inside of that consume that gets stored, there's another produce. That produce doesn't actually happen until this produce right here. So the first thing that would happen is that this consume would get stored in the store, or so this receive would get stored by virtue of it being called by consume being called. Then this would happen, calling produce on the store, and then this message would come through here, and then there'd be another call to produce. So it maps pretty directly onto Erlang sends and receives that way. And then this has been brought up a couple times. You've even seen the Standardout channel if you were paying attention in Kyle's presentation. We have this way of essentially, I mean, I say effectful code. You could potentially put non-effectful code, but I'd like to prefer to think of, doing anything in Scala we can think of as an effect in this case. It sort of like keeps the notion of Erlang kind of pure that way. So printing the standard out and standard error, these are just Scala functions. And that tag continuation type we use means that we can dispatch based on what type of continuation we find. So if you send a message to Standardout with a string, it will print out. We're going to have one for reading and writing from the file system. Eventually, hopefully with the help of DAP-Hub, we will get some network communication happening. And then the FFI that you've heard about as well will also be done this way as well. So these first three are what we call static system processes. They're hard-coded in Scala. And then the fourth one is what we call a dynamic system process. So,
any questions on that? Kind of like.
You want?
Oh, there's a question.
Oh.
Okay, so at the beginning of the presentation, there was this table where, depending on whether the persist flag is set to true or false, you can have different behaviors.
Yep.
So we can based on some combination of this flag, you can get the like regular key value store, like any other behavior. And once you add the network communication, this RSpace get replicated across nodes.
The network communication that we're talking about here would not be replicating RSpace across nodes. Okay. It would be more like you just wanted to send a UDP or a TCP message of your choosing somewhere, and so you would produce on some given channel. Okay. And you'd have that message as the argument to that. Some caveats, acknowledgement, channel, et cetera, et cetera.
But once, I don't know if I understand that correctly, but once the consensus is achieved, then does the consensus converge also on the representation of the RSpace?
This is like kind of a separate thing than the consensus communication, right? Like Casper will be doing produces and consumes itself for the sake of consensus. So we can just imagine this. I mean, we don't even have to think about this as being communication with another node. I say communication with the outside world. Yeah. So it could be like you want to write a HTTP server as a system contract in Erlang. You could use this system process to implement that code in Erlang that way.
So what I think the miss here is we're talking about, we want Erlang to be a general purpose language. If you want a language to be a general purpose programming language, you have to be able to create effects on the machine or on the server on which you're running your application, right? So we have Erlang as a blockchain language where we do not want contracts to create any effects on the node for security reasons.
None of these things would be running in smart contracts on the blockchain.
And then you have this other side of Erlang where you want Erlang to be a general purpose language where if somebody wants to use the RChain node to write a web server, they can do so via the system processes mechanism.
So system contracts is a pivotal word here, and that hasn't really come up before now, maybe only in passing. But we make this distinction between system contracts and blockchain contracts. Sometimes people don't even use blockchain, they just say smart, but I'm going to say blockchain because it helps.
Yeah, what I had in mind was using just the RSpace as the standalone library, so it could build. Yeah.
In the case now, what we're talking about here, the system processes as a standalone library, this is actually partially implemented in the Erlang interpreter right now. We've had some discussion about maybe splitting that out into a separate component. If you were going to do this yourself, you'd want to use a tagged continuation type like we do. So it's to say that where we use a protobuf and we have two separate types. So one of continuation, one of them is a Rolang continuation. The other is just an int64 that goes to a lookup table to Scala code. You would want to implement a similar thing if you were doing that. So you could wrap something like that serialized byte array that you saw, or basically serialized continuation that you saw in the example, into some kind of tag continuation type, saying, oh, okay, that's my language's continuation, or that's my project's continuation, but then here I have another type of continuation that I also want to be able to run, given something else. You could use Jython in your JVM, and you could have a Python continuation, and you could like have a tag continuation serialized into that Python continuation. Like, really ridiculous example, but I mean, that's like motivating the use case we have in Rolang, and where we want to be able to run both Rolang continuations in the context of the interpreter and the context of that execution environment, as well as Scala code, right? And then eventually Rosette continuations as well.
Okay, thanks.
Any other questions?
Here's Standardout in action. Pretty simple, yeah. And then this is, you actually saw this in Kyle's slides as well. This is Standardout with an acknowledgement channel passed to it, so that you can basically say, oh, okay, once I've run Standardout, then I want to just send something to this acknowledgement channel saying, I'm done. It's like a nil process, I think. And then ACK gets that, and this runs after Standardout ACK goes. So this is like the common pattern. Again, like Kyle, can't reiterate this enough. Like, you want to write sequential code because that's maybe how you're used to writing code. So internalizing this acknowledgement channel model is like pretty crucial to successfully writing Rolang.
That's the last slide.
Is it?
It is.
All right. That's it.
Have questions?
Any more questions? Okay.
Okay. Short and sweet. Oh, Kyle. Okay. Go ahead.
So one of the cool things you can do with the acknowledgement model is if the answer you want to give back is the result of something else, you can include tail call optimizations in your own code.
Ooh, fancy. Yeah. So the interesting thing, Kyle mentioned this, is like if you go and you look at that part of the Rolang interpreter, there's a very simple dispatch table. There's a map between these int64s and these Scala closures, these Scala functions. Inside of the function bodies of those, what we're doing is we're actually constructing Rolang terms. So this is like the border between Scala and Rolang, where you get something back from some Scala, Java library, et cetera, in the context of your static system process. You then need to make that into something that Rolang recognizes. So,
do you want to show us that?
Sure. I might do a little bit better on the Mac. I don't know. Let's see.
Let me go to mirroring.
I can do it with mirroring. Without mirroring.
No, it's okay. I'm going to go dev.
This is a Rolang source. Scala. Yep. And then runtime. Down, down, down. Down, down, down. Okay, that's good.
Can we see that?
Right. This is the dispatch table that we speak of. Our 0 process is Standardout. Our 1 is Standardout ACK. 2 standard error. 3 standard error ACK. I don't remember where we put system processes. They're in another file. Go to those. It's going to be in the same directory, and it's going to be called system processes because I wrote it. So these are the actual static system processes here. Now you see what the way this works, right, is that in the Rolang world, data is actually a sequence of channels. You don't have to concern yourself with that, but just know that that's what their A-type is in that case. So the functions that we need to use in this dispatch table, or we need to use the dispatch here, need to take that as their argument. Now, this one is just returning unit. In fact, a task of a unit, because we're running this in the Monix task. But if we look at ACK here, you can see, do these do unit as well? You know, we didn't actually put Rolang in the return types of those, did we?
No,
it's through the dispatch, isn't it?
No.
Yeah.
You're sending Rolang on the return channel. It's on line 20.
Line 20. You're talking about when we dispatch.
No. Line 20.
This is a match.
No. Line 20.
This here?
Yeah.
This is this call to produce here.
Yeah.
Right.
We're sending par.default instance. That's the nil process.
Right. That's the part where we're talking back to Rolang, but it's the dispatch back into the Rolang where the thing that comes back through Standardout ACK. Like that's the actual border right there.
Yeah, so if there is a continuation rate waiting, we'll hand it back to the dispatcher.
Right.
So it's either another Rolang continuation.
Right. Oh, I see. Yep.
So you could pass, quote, Standardout to as the acknowledgement channel, and then you would print out the nil you got back.
That's right. Okay. We're riffing over here. Does anybody else have any questions?
I have a question. Grab the mic right next to you.
Hi, it's Kayvon. Just overall project structure. What is the reasoning behind wrapping all of these different projects under one SPT build?
Oh.
Rather than, since you're targeting this for not just Rolang.
Mm-hmm. Why did we do that, Medha?
Our desire is to have ultimately a single package to install the RChain node that contains within it all the dependencies that a developer could possibly need to do whatever they need to do with the software. It's the first reason. The second reason is when we started packaging up Node that we decided to unify all the projects underneath it.
If you're familiar with multi-project SPT builds a little bit?
I'm just curious as to wouldn't that create an artificial dependency between projects that have nothing to do with each other? No,
thankfully in the case here, if you were going to download the jar of this, if you're going to put the coordinates, the dependency coordinates in your SPT file to fetch this from Sonatype, the jar that you get does not depend on any other projects except not this code, but this is Rolang. But RSpace does not depend on any of the other projects. Yeah.
If you're asking about the RSpace library, there are no dependencies with the core Rolang of the core RChain project.
That's right.
That library is separate.
RSpace is at the top of the dependency chain in that regard. So you don't have to worry about incurring a dependency on any other bits of the system that you wouldn't need. This dispatcher stuff is entirely separate. That's part of the Rolang implementation. So we had to make a bit of a quick decision about choosing efficiency of single top-level build versus having individual builds. It eliminated some redundancy in our SPT files. We got to do more sharing of things. We got to make sure that we were all using the same dependencies, which is big because we had, 6 different projects.
And the goal is to ultimately get to build hermeticism.
Yeah.
For security reasons, for a variety of reasons. So we'll be doing some of that.
This is a story. This is definitely, we're going to be working towards getting deterministic hermetic builds. We have some ideas about integrating SPT builds with Nix. If you guys are familiar with Nix, project that personally I'm a big fan of, but I've been going around selling this to everybody else. But there isn't great out-of-the-box support for meeting those two worlds, SBT, dependency resolution and management. There is one project that I'm pretty excited about giving a whirl with. But yeah, the build story is evolving. At this stage in the game, I think we like having a mono repo, and I think we like having a top-level build in the mono repo. But understandably, when we're splitting out some components as libraries, there's always that tension of having this modular component and then having it exist in a giant mono repo as well. So,
any other questions? If you think of something later, you can always catch us at the conference or later on in Discord. Thank you.
And please criticize and comment and file bugs and anything else. Yeah, because like
love feedback. Yep.
Yeah, we love feedback. So yeah.
Thank you.